So now what I'd like for you to do is work on these practice problems. I've given you a set of practice problems here. A, B, C, and D. And I'm asking you to fill in the correct coefficients for the blanks provided. And then over here on the right, I'd also like for you to see if you can identify the type of the reaction it is. And you can just put an abbreviation for the reaction type. So we're helping you to develop that skill of identifying the type of reaction. So pause the video now and do these first four. And when you're done, continue the video and I'll work through them for you. So just A, B, C, and D. Go ahead and pause the video now and do those. Okay, I'm assuming that you have given it a shot, tried to balance these. So here we go. We're going to start with A. We're going to be methodical. Oh, first, before we do this, let's see if we can identify the type of reaction this is. From our 6 basic reaction types, this looks an awful lot like a hydrocarbon reacting with an oxygen to form CO2 and water. And that is a classic example of our combustion reaction. Notice I wrote out the whole name here. I didn't just abbreviate it COMB because we have another reaction type called combination. And if I had just used the first 4 letters, it would not have clearly indicated which reaction type it was. So we've got a combustion reaction here. Hydrocarbon reacting with oxygen gas in the air to generate water and carbon dioxide. By the way, it does not matter which order your products are written in. I could have written water and then carbon dioxide or carbon dioxide and water. As long as I have the correct formulas for them, it doesn't matter which order they're in. So here we go. We're going to be methodical about balancing these. We're going to go to the far left and go element by element, or if we see a polyatomic ion that remains a polyatomic ion on the product side, we'll treat the whole ion as a single species. Doesn't look like I've got any polyatomic ions in this though. But here I have 3 carbons, 1 carbon. So I need 3 carbons. Methodically, shifting to the next one. 8 hydrogens, 2 hydrogens. If I put a 4 here, now 4 times 2 is 8. So now I have 8 hydrogens. Now I changed the coefficient, so I'm going to go back to the beginning and see if I need to correct anything. 3 carbons, 3 carbons. 8 hydrogens, 8 hydrogens. Good. 2 oxygens on the reagent side. How many oxygens do I have on the product side? Take a moment and see if you can count up how many oxygens there are on the product side. Do you see 6 of them? Do you see 10 of them? I see 3 times 2 is 6 right there, and 4 more right there is 10. So I've got 10 oxygens on the product side. 2 over here, 10 over here, so I need a 5 right there. Now I have 10 oxygens. Now again, I've changed the coefficient. I'm going to go back to the beginning and see if I need to fix anything. 3 carbons, 3 carbons. 8 hydrogens, 8 hydrogens. 10 oxygens, and 6 and 4 more is 10 oxygens. So that is balanced. Now you'll notice that I did not put a 1 here for this coefficient. Many of you may have been taught in your previous chemistry course to write a 1 as a coefficient. And the reason that instructors ask you to do that is that they want to make sure that you know that there is a 1 understood there. And so they ask you to write it there so that they know that you know that there's a 1 there, and not just that you have forgotten to balance that or that you have just left it blank. However, moving forward in this class, if the coefficient is a 1, we will not write the 1. We will leave it invisible, and it will be understood to be a 1. So our coefficients here are 1, 5, 3, and 4. Moving on to the next one. This looks like a single standalone element that is reacting with a compound, and it looks like that single standalone element is kicking something else out to become a standalone element and taking its place in the compound, and that is a single replacement. And I could abbreviate that SR because there's only one of the 6 basic chemical reaction types that has that abbreviation. Okay, starting from the left, 1 zinc, 1 zinc, 1 copper, 1 copper, 2 chlorines, 2 chlorines. Everything is already balanced, and sometimes it happens that way. Sometimes you won't have to do anything at all. That equation is already balanced. Moving on. Here it looks like I have an ionic compound and another ionic compound. This is ammonium hydroxide, that is magnesium sulfite. And it looks like that when they reacted, they switched places. The 2 cations switched places. So now the ammonium is going with the sulfite, and the magnesium is going with the hydroxide. And that is a classic example of the double replacement precipitation reaction. So let's balance it. We're going to go to the far left and be methodical again. So if you look at this NH4, we recognize that that's an ammonium ion, and we have ammonium ions over here on the product side. So we're going to treat the ammonium as a single species. We're not going to individually balance the nitrogens and then look at the hydrogens. Instead, we're going to look at ammonium, NH4, and we have 1 of them here, and we have 2 of them here. So I need 2 ammoniums over here. 2 ammoniums, 2 ammoniums. Same thing with the hydroxides. I've got hydroxide over here, and I've got hydroxide over here. So it appears that the hydroxides are staying associated, staying stuck together. So here I've got 2 hydroxides. Here I've got 2 hydroxides, and the hydroxides are balanced. We move on to the next one in the row. 1 magnesium, 1 magnesium. And then next, the sulfite is here, and it stays stuck together, so it's a sulfite. I have 1 sulfite here, 1 sulfite here, and it's balanced. So it looks like the equation is balanced. Let's confirm. 2 ammoniums, 2 ammoniums, 2 hydroxides, 2 hydroxides, 1 magnesium on the reagent side, 1 magnesium on the product side, 1 sulfite ion on the reagent side, and 1 sulfite on the product side. So sure enough, it's balanced. We're going to move on. Starting from the far left, 1 barium, 1 barium. Are these hydroxides still hydroxide? Oh, they are not. So what kind of reaction is this? Well, notice I have a hydroxide containing compound here and an acid here. So there's my base and there's my acid. So this is an acid-base neutralization. And we know that in an acid-base neutralization, I very often form water as a product. So that hydrogen from the acid and that hydroxide from the base are going to pair up to form water. Now I'm going to use a method here that I pointed to earlier, I'm going to write that water molecule like this, as an H bonded to an OH. And what that's going to do is it's going to allow me to balance the hydrogens from the acid and the OH in the water that came from the hydroxide in the base separately. So I'll treat them as separate species. This is the only time that it really helps to do this, but you'll see how it helps us balance this. So here we go. I have one barium, two hydroxides from the base, one OH in the water that came from the base. So again, two hydroxides from the base, one OH in water that came from the base. So I need two of these, don't I? The way that I get two of them is I put a 2 right here. So now I have two OHs in water that came from the base. Now this OH in water is not a hydroxide ion. These are not ions. I'm just drawing it this way so I can emphasize two different parts of the water molecule separately. So one barium, two OHs, hydroxides from the base, two OHs in the water molecule that came from the base. One hydrogen, and when we are balancing the hydrogens from the acid, we don't look at any hydrogens that may be in the anion. We just look at the initial hydrogens. So there's one initial hydrogen here. So one hydrogen from the acid, and here we have two hydrogens in water that came from the acid. So again, one hydrogen from the acid, two hydrogens in water from the acid. So I need a 2 there. One barium, two OHs from the base, two OHs in water from the base, two H's from the acid, two H's in water from the acid, and that's the acetate ion. Two acetate ions and two acetate ions. So it looks like the equation is balanced. So this 2 that I put down here, that's what needs to be right up there, right? All right, so that's a little bit of a trick that we can use to help balance acid-base reactions when I'm forming water. This, writing water like this, really only helps us when we're doing acid-base neutralizations. When we're dealing with water as a product of a combustion, there's no need for us to write it like this. Again, the only reason I'm writing it like this is so that I can keep track of the H's, the hydrogens that came from the acid, separately from the OH's in the water that came from the base. Okay, so there's an example, 4 examples of a combustion, single replacement, double replacement precipitation, and acid-base neutralization.